S. presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
In part 1 of this video, we have already described about Schrodinger's equation, and we will now continue to look at what sense does Schrodinger equation makes and how do we draw the actual shapes of electronic clouds present inside the atom. So we're now going to visualize how this Schrodinger equation, which we looked in part 1, is going to be useful and how we can draw the actual probability diagrams, which we call orbitals, for a specific electron in an atom. Welcome to S. Academy. My name is Aditya and you're watching engineering chemistry videos. If you want to learn more about this topic, you can refer this book from S. Publishing. You can find link for ebook in the description box below. So here you can see that psi square, which can be represented by probability distribution. On the other hand, you can also see that it is possible to deduce a wave function for a specific electron in an atom. So what you know already from the previous models, that there will be a central nucleus and there will be something called as first orbit, then there will be a second orbit, and then there will be a third orbit. So electrons are spinning at a specific distance from the nucleus. This is known from Niels Bohr model. Now, if you like to treat this electron which is present in the first orbit, it will have its specific electronic distribution or probability. So this electron can be found everywhere around the nucleus at a specific distance, or you can say at a specific circumference, and in the form of a wave. And that wave function can be defined in terms of the charge, in terms of the atomic number and the radius. It can be explained with the help of this derivation from the Schrodinger equation. So we can get a wave form, or we can get a probability distribution, which you see here in the form of a cloud. Now, what these dots represent, they actually represent the electron is present at the same time at all these positions. So it is distributed all over the place, and we call it as 1s. That means within an orbit, when there are multiple electrons, they form the clouds, or they form waveforms, which are explained by wave functions, and their specific positions or probabilities can be drawn practically, which we call as orbitals. So orbital is what? Orbital is basically a probability diagram that is representing psi squared values for specific electron. And as you move to the next and next orbit, you will again encounter the s orbital, and if you move to the second orbit, you will have many more orbitals inside the orbit, because there will be many electrons and there is a likelihood of positive or constructive interference and destructive interference. So these interference along with the electrons that result in developing various probability shapes of orbitals, and this is how orbitals are represented. Now, one thing is important: when you move from 1s to 2s, you will see an area of low probability. What you can see here, in case of 1s, it was a solid sphere. That means probability of finding electron was like a spherical, in a spherical space. But when you move to the second orbit, the electrons of the second orbit will have a very well defined probability in an area, but they will also have a probability 0 at the central part, which was already occupied by 1s. So you can say 1s electrons were present in this space where 2s electrons cannot be found. The electron of second orbit cannot move into the space that is already occupied by 1s because of energy differences. So this area where you cannot find, or where the probability of finding an electron is 0, is defined as node in these probability diagrams. Similarly, when you move to third orbit and when you look at 3s electrons, these 3s electrons will have a high probability region at a specific distance from the nucleus, but They will not be present in the region which was occupied by 2s electrons. They will not be present in the region occupied by 1s electrons. So there will be basically two nodes in 3s orbital. So 3s orbitals will be a big hollow sphere with two zero probability regions, whereas 2s orbitals, they will be solid sphere with one low probability or zero probability region. So even if the electrons are present in S orbital for the first orbit will be different than the S orbital for the second orbit and S orbital for the third orbit. So that is what we could deduce from the Schrodinger's equation, that is shape of orbitals. Now further adding to this, how many different orbitals are there and how we can represent. So one way of representing these orbitals was in the form of actual probability shapes. We can represent in the form of clusters of dots. High density areas, they are representing more probability of electrons, and low density areas are representing low probability or zero probability of electrons. Whereas they can also be represented in the form of a graph. Instead of representing in the form of a dot plot, like this was for 1s, we can also represent it in the form of a graph. Now, what does this graph depict? This shows that at a certain distance from the nucleus, which might be in angstrom, the probability of finding electron is very high. But as you move away from the nucleus at a specific distance, you will never find that 1s electron elsewhere in the atom. But when you talk about the second orbit, you can find the probability of second 2s electron, little bit probability here, and then a node, that means zero probability, and then a high probability of finding electron at a specific distance, which is almost equivalent to distance of the nucleus until the second orbit. So this is the second orbit, and let's say from here to here is the distance of second orbit. So this distance is represented by this distance here in this graph. That means the electron is likely to be present at this position according to the classical model, but according to the quantum mechanical model, there is a probability rather than having a specific point of electron. So it is distributed elsewhere also. It may be present here, it may be present here. So around the entire circumference, this electron may be distributed everywhere. And there is a slight probability also somewhere here where this 2s electron can be present, but in between there is a node and there is zero probability region. Similarly, when you go to the next orbit, that means orbit number 3, so you will have a slight, very little probability region here overlapping with 1s, then another probability region just between 1s and 2s, but the highest probability region that will be farther away from the nucleus, which is represented by this point. So what sense we can make out of it? Electron is not a point. Electron does not move in a straight circumference just like a particle. Rather, it is a wave, and that wave is present at more than one place, or that is present in the form of a cloud. We can only have the probabilities of finding those particles in the wave rather than looking at distinct or unique particles. So that is the sense which comes out from the Schrodinger's wave equation. And here we have seen two different representations. One representation is in the form of this scatter plot, which is showing the probability of finding electrons. And the second one is through this typical graph where you have probabilities on y-axis and distance from the nucleus on x-axis. Now, let's talk more about orbitals. So, you know, orbits are specific distances where electrons are present in the classical model, but now we learned that according to quantum mechanical model, electrons are not only spinning in specific orbits, but their waves are collectively forming orbitals. And as we move from first orbit to second orbit, we will notice that the number of electrons keep on increasing. If you look at the simple noble gas configuration for the helium, you would find 2 electrons which are present, or which is the maximum number for first orbit. But as you move ahead, you will find that there will be 8 electrons, and as you move further ahead, you will have 18 electrons. So the number of electrons in each subsequent orbit keeps on increasing. Now, if you look at in the light of Schrodinger's wave equation or the quantum mechanical systems, then you will realize that this is not a particle and this is a wave, and there are 2 waves in this place. There are 8 waves which are at the same place. So you can say one wave in the space and another wave in the same space, yet another wave in the same space. So such 8 waves are present, which are revolving, which are present at around the nucleus at a specific diameter. So they will have kind of interference with each other. And these waves will not be independent, but rather they will combine together and they will give rise to new probability diagrams or new probability shapes. That means new type of orbitals. So as you keep on moving, in the first orbit, you only have one type of orbital which is called as 1s orbital. But as you move ahead, there are 8 electrons here. So you are likely to have s orbital as well as another type of orbital which is called as p orbital. The farther you move, as you go to third orbit, you will not only find s, p, but yet another type of orbital that is called d orbital. And even if you move further, if you further move ahead on the fourth orbit, then you will find S, you will find P, you will find D, and you will find F. Now, why these different orbitals are arising as you are moving ahead in the next orbit? Because there are more electrons and there are more combinations of these electronic waves. These waves are combining to give rise to new probability diagrams, and therefore you have various shapes of the electronic clouds. Now, how do they look like? We have already discussed about the simplistic model of s orbital. Is p orbital also of same type? No. They are symmetric, but the shapes of p and d vary. So if you try to compare these shapes, I would say s orbital, irrespective of which orbit it is present, is always spherical. So you can represent it in the form of a sphere where you have probability of finding electrons at a specific position from the nucleus. It is a different thing that for 1s, it will be a solid sphere. For 2s, it will be a sphere with a node. For 3s, it will be a sphere with 2 nodes in it. Whereas p will be more or less dumbbell shaped. So p orbital will not have a probability distribution in a spherical manner, but it will have a probability distribution in a dumbbell shaped manner. So whereas the node in case of 2s was present in the center, this was the node area, which you cannot see if you are imagining that cloud as a sphere. You can see that node very distinctly in the p orbital at a midpoint. So this is basically node for p orbital. And another thing is that p orbital is not only present in one axis, it is symmetric, but it is also degenerate. That means if one orbital is present across y-axis, there is also an orbital which is present across x-axis, and there is also another orbital which is present across z-axis. So we can say 3 symmetrical degenerate p orbitals may be found which can accommodate electrons in the third orbit. This will be represented by py, px, and pz. It is important to remember here that energies of all these 3 orbitals will be equivalent. That means electron will have a choice to go here or here or here, and if electrons is present in any of these waveforms, will have equal chances of interacting with another atom or another molecule, since they have equivalent energies. So energies are equal, there is a degeneracy, you can club them, you can combine them, and you can represent the entire p orbital like this. So there are certain rules of filling of electrons in these orbitals. Also, you might have learnt about Pauli's exclusion principle and Hund's rule in classical chemistry, where you know that each orbital can accommodate only one electron in one spin. So at maximum, with opposite spin, an orbital can accommodate two electrons or a pair of electrons. So two electrons here, two electrons here, two electrons here. That means whenever you are writing electronic configuration, you can always write it like 2p2, 2py2, or 2pz2. That is the maximum number of electrons you can accommodate in p orbital, or collectively you can call it as 2p6. So if you are willing to know that how electrons will be filled in carbon atom, so carbon is having atomic number of 6, and its first orbit will have 2 electrons which will be filled or present in the form of s orbital, whereas remaining 4 electrons will be present in 2s orbital, 2 electrons on the 2s, and remaining 2 will be present in p orbital. But keeping in mind the Hund's rule of maximum multiplicity and Pauli's exclusion principle, we can say that these 2p electrons will be singly filled in px and py, whereas pz will be empty in the carbon. So this is how the new model of atom in light of quantum chemistry explains the presence of electrons in different electronic clouds, which are called as orbitals. Similarly, you can go higher and you can talk about d orbitals. So since d orbitals will be formed by a more complex network, if you go to the next orbit, that is third orbit, there will be so many electrons, so many waves. So when there will be so many waves, there will be more complex patterns of interference that will be formed, and that can be represented by more complex type of orbitals, which are called d orbitals. And just like p orbitals were degenerated into 3 types, d orbitals are degenerated into 5 types. So they are represented like this. They have a double shape. So there is dxy, there is dyz, and there is dzx. Keep in mind that the x's are different. Here it is x and y, here it is y and z, here it is x and z. So these 3 are one type of d orbitals, and then there are 2 more, or one is called as dx square minus y square, and then yet another type of d orbital which is called dz square. So in total, there are 5 different type of d orbitals, and that is the reason why d subshells can accommodate 10 electrons in total. So you can keep on filling 10 electrons in these orbitals. Now, one thing that is very, very important to note here and to remember here, it is difficult to compute or difficult to use this Schrodinger's equation for complex multi-electronic atoms, because as you go ahead, the number of electrons will increase, and apart from the wave functions, there will also be electronic repulsion that will exist. So it is quite complex to calculate those electronic repulsions. Therefore, most of the orbital shapes, which are even known for multi-electronic atoms, they have been calculated by considering only hydrogen-like atoms. So single electronic assumptions have been made to explain the shape of all these orbitals, which we presume to be present in all the atoms. So I hope this point is clear to you. You understood that how we came to get the idea or the picture of probability distribution of electrons inside the atom, which looks like orbital. Now, all these assumptions were based on one fundamental concept, which is called as particle in a box concept. So what does this particle in a box concept means? This actually is a kind of hypothesis which helps you to realize or which helps you to understand that how waveforms are formed and how they combine together. So we generally imagine a box of such a small dimension, so that the particles are not particles there are capable of representing their actual waveforms. That means if you imagine a box model, which is also called as infinite potential well or infinite square well, here the particle is free to move in a small space surrounded by impenetrable barriers. So you can say if you have a particle in the open space, it might slow down or it might stop, it might hit with other particles. But if you are having infinitesimally small box where the particle is free to move and there are impermeable walls, then it will be actually realizing the Schrodinger's equation, and it will be capable of forming the exact waveform which is required for explaining the model of an atom. So that was all. I hope you got the glimpse of Schrodinger's equation and you understood what Schrodinger's equation stands for and how this equation is useful in deducing the basic structure of atomic orbitals. If you want to learn more about this topic, you can refer this book from S. Chand Publishing. You can find link for ebook in the description box below. You can like, share and subscribe the channel for continuous use and regular updates.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.